Okay, so here we are still in chapter 3.9, and we're going to be talking about the work that's going to be required to pump water out the top of this crazy shaped tank. Okay, so this tank is a right circular cone, and it's put so that the vertex is at the bottom. Okay, the radius at the top here, at the widest spot, is 8 feet, and the total height of our cone is 17 feet. Now there's water in this tank, and it's filled up to a height of 13 feet. And the density of water, right, our weight density of water is 62.4 pounds per cubic foot. We want to calculate what's the work required to take this water out the top of the tank. Okay, so we have to remember our work is force times the distance. So we have to take this into pieces, right? And again, what we're going to be doing is we're going to take tiny little slivers, circular slivers. I'm going to take that tiny little sliver that has a tiny little thickness, dy. I'm going to move that sliver out. Okay, and move it whatever distance I need to move it. Okay, so I'm going to think about the area of my circle is pi r squared, and I want to be able to move it some kind of a distance, right? This is going to be the height that I'm going to go. But I have to think about my radius, right? First, let's take a look at the radius. Because the radius at the top, 8 feet, isn't the same thing as the radius here. Radius here is much smaller than that. So I have to come up with an equation that's going to relate the radius as a function of the height. Okay, so to do this, I'm going to do similar triangles. I'm going to think, well, geez, at the top, my radius is equal to 8 feet, right? And when that's true, my total height is equal to 17 feet, right? So I'm going to solve this in terms of x. So I'm going to get x equals 8 times y all over 17. It basically gives me a function for the radius as a function of its height. Okay, so then I can plug that into here. So then pi r squared becomes 8y over 17 squared. Okay, now the distance that I need to travel, again, we talked about this in a previous example. So my total height of the tank is 17 feet, but the water that's here at the top of the tank isn't going to go the same distance as the water that's at the very bottom. So I need some kind of a function that's going to tell me how I can think about the height as a function of where that particular sliver is. So my total height is 17 minus where I happen to be in that tank. Okay. Now our work to do this, right? We were told that the water was filling up the tank up to 13 feet. So I'm going to do all the water from 0 up to 13 feet. So this tells me basically what volume of water I'm going to be doing. So I'm going to put in my density, which is 62.4. Okay, and now I'm going to be putting in my pi r squared. So this is going to be pi. Let's see, I'll get rid of the parentheses here. I'm going to go 8y over 17 squared. And then I'm going to put in my height, 17 minus y. And I've got my tiny little thickness of each circle, dy. Okay, so I'm going to multiply through. I'm going to have to square this 8 times y quantity squared over 17 squared. Okay, so when I do that, I'm going to multiply it by 62.4, and I'm going to start distributing things out. So this is going to look like, I'm going to put it in decimals, 3993.6 times pi all over 289. That's our 17 squared. We're going from 0 to 13. Okay, now I have y squared, that comes from here, times 17 minus y dy. I can distribute my y squared to all of these and then use the power rule to actually integrate. And this is a 9, 0 to 13. So this is going to look like 17y squared minus y cubed dy is going to give me 3993.6 pi all over 289 times 17 over 3 y cubed minus y over to the 4th over 4, and I'm going to go from 0 to 13. And when I do this and I multiply it all the way out, I get 73,369.06 times pi. And we'll call that in joules. Okay, that's the work. I can multiply it through by pi if I want to, or I can leave it in terms of pi.